Okay, so this is section 3.9. We're going to learn the last two derivative rules that we need for the exam. So here we go. The first one you'll see here is we're going to take the derivative of a random sort of exponential function. So we learned the derivative of e to the x. So we know the derivative of e to the x is e to the x. But now this is for some random a. So for example, the way to apply this rule, like the derivative of 2 to the x maybe, we would say is 2 to the x ln of 2. So you could use this for any a this time, not just e, but also for some exponential function that's not e to the x. You might be wondering where that comes from, and there's a few things you could do, but we'll use this. We'll prove it based on the fact that we know the derivative of e to the x. So a you can always rewrite as an e times ln of a, or e raised to the ln of a to the x. Because ln of a, e to the ln of a is the same thing as a if you use your log rules and cancel the fact that those are inverse functions. So this is really e to the ln of a times x. And so if you're going to take the derivative of that, you get e to the ln of a times x, but then you need to multiply by the derivative of ln of a times x using the chain rule that we learned in the last section. So the derivative of that shows up here. And so that really gives us y prime. Remember, this simplifies back, this first piece here simplifies back to a to the x, so we get a to the x. And the derivative of ln of a times x, this is just a constant times x, so you get times ln of a. So that's where that derivative comes from. And then the generalized form, kind of similar to how we have a generalized form for exponential functions. If we want to take the derivative of a raised to some function, it's really just the chain rule. So remember, you're going to have this, your original derivative. So that's the derivative of a to the x. So the derivative of a to the f of x, we leave it with take the derivative of it, but leave the inside alone. And then multiply by the derivative of the inside, which is f prime of x. So that's your derivative for a general exponential function raised to some other function. So let's see. Our example is we want to take the derivative. So f of x is 2 sine of pi x. So if we want to take that derivative, f prime, we're going to write down exactly what we started with. Don't forget your ln of 2, and then we want to multiply by the derivative of sine pi x. And so if we're careful here, we get 2 sine pi x times ln of 2. Derivative of sine, remember that is cosine. This is another kind of chain rule thing, so we have cosine pi x, but then we need to multiply by the derivative of pi x. And so your final answer here, run a little bit out of space, but oh no. I've run a little bit out of space, but maybe we can put the answer up here. So our final answer is 2 sine pi x times ln of 2 times cosine of pi x, and then all of that is times pi. So there's your final answer for the derivative part. Okay, now we're going to do some derivatives of logs. And in order to do derivatives of logs, the first thing we need to do is remember all of our log rules from back in the day when we first learned about logs. So remember, multiplication of logs turns into addition of logs. Division, a divided by b, remember that turns into subtraction. And finally, if you have a to the r, you can take your exponent and take it down front. And these all should look familiar, like if you're thinking about, if you have something like a to the x times a to the y, what do you do to those exponents? You add them. So this idea of logs, they're really just the same as the exponent rules that you all do really well with, but they're just converted into logarithms. So multiplication inside turns into addition outside. So here's the multiplication on the outside turns into addition on the inside. So it's kind of the inverse kind of way, right? So what was once on the outside is now on the inside, and vice versa, because these logs and exponents are inverse functions of each other. Similarly, this one, you hopefully all kind of have been doing this. If you have ax divided by ay, you know that you subtract exponents. That's a similar thing. So if you have division inside, you know that you can subtract it as a log. So that's kind of where these rules come from. And the big thing to also keep in mind is to remember that you cannot do anything with this ln of a plus b, and you cannot do anything with ln of a divided by ln of b. These things do not simplify. So make sure you don't attempt to simplify those things. You have to leave them exactly as they are. So now, as we start thinking about derivatives and what we might get for derivatives of logarithm functions, we can talk about the fact that the derivative of a log that has any random base, a, is 1 over x, and then times ln of a. And the derivative of natural log, which is our sort of favorite friend, is just 1 over x. And there are a few ways to show that. You can do some of the stuff that we did with inverse functions in the last section. Another thing you can do is kind of follow along here. So if y equals ln of x, then you would have e to the y is equal to x if you take the e of both sides. And then if we take the derivative of this using implicit differentiation, which we haven't actually studied yet, but we'll see soon, you would take the derivative of this, dy dx, that's the derivative of y, and that's equal to 1. So I took the derivative of both sides and got that dy dx is really equal to 1 over e to the ln of x, 1 over e to the y, and y is ln of x. So in other words, the derivative is really just 1 over x. So the only thing that's kind of a little bit strange here is this, this term right here you might be a little bit confused about. But the idea is that we took the derivative of both sides, and the derivative of x is 1. And the derivative of e to the y is e to the y, but there's kind of like a chain rule thing happening because we have this y here. So we take the derivative of y with respect to x and put it right out front. So it's very similar to a chain rule thing. We're just multiplying by the dy dx because we don't know the derivative of y with respect to x, but we want to include it in our process. So now we're going to use these rules and practice taking a couple of derivatives just to make sure we feel comfortable, and we'll do a couple more in class. But let's see what we get as examples. So the first one we want to take the derivative of, let's say f of x is ln of x plus 1, that whole thing raised to the 5th. So there's a few things you can do. Hopefully the first thing that you recognize is that this is a derivative of a log, and in particular it's the derivative of a logarithm that's actually a chain rule question. So we have to think a little bit about the chain rule. So there's two sort of options. The first is to go ahead and do this chain rule thing. So remember the derivative of log is 1 over the inside, so x plus 1 to the 5th, and then we would multiply by the derivative of the inside. So this is our derivative. Okay, if we were to simplify that, we'd get 1 over x plus 1 to the 5th times, again, this is another chain rule, and then this would be our answer here. You could simplify that and make it much nicer, but that's one way to do it. The other way, sometimes with logs, you can actually start by simplifying it. You could take this exponent out front using our log rules, and then your derivative becomes a little bit easier, because now if we were taking the derivative, we get 5 times 1 over x plus 1, and then times 1. So you just get 5 over x plus 1, which is a little bit nicer than having to take the chain rule stuff over here. So with logs, you can always try to think and see if there's a quicker or easier way to do the derivatives. Another example that we'll do is this one here, just kind of thinking about some of our other rules. So this one we have natural log of the sine of x times sine of ln of x. So hopefully you recognize we're going to need the product rule for multiplication, and then each of these is also going to use the chain rule. So if we start taking this derivative, we're going to start by just writing the first term times the derivative of the second, and then plus the second term, don't do anything to it, times the derivative of the first term. Okay, so we have all of that. Now we're going to go through and take these derivatives. So the derivative of sine of ln of x, so remember that's the derivative of the outside, which is cosine. Leave the inside alone, and then times the derivative of the inside. That's your chain rule. And then this one stays. And now we're going to take the derivative of ln of sine. So that's 1 over sine. And then don't forget we have to take the derivative of sine, which is cosine of x. There's no x in this sign. It's sine of ln of x. Okay, so we went through, and hopefully you can kind of see this turned into this entire derivative, and over here, this derivative is all of this part here. So just don't forget that each of these was a chain rule, so this was a derivative of this bottom, the inside piece, and over here, 1 over x was the derivative of the inside of ln of x. So you could leave your answer like that, that would be just fine, and that's the solution to that first page. That first example. Let's do this one other example. We have the room right here, but we will try to do this one other example. See if we can just get some space. So this is number 2. We have that g of x is ln of e to the x plus ln of x. So if we want to take that derivative, all right, so here's our very last derivative, g prime of x. This is ln. Remember, this all goes in the denominator because the derivative of ln of x is 1 over x. So it's 1 over all this times e to the x plus ln of x derivative. So if we're finishing this up, we get 1 over e to the x plus ln of x, and then the derivative here, derivative of e to the x is e to the x, derivative of ln of x is 1 over x. And we are finished.